We are getting close. We are in Chapter 7 of CCNA 4, second to last chapter on network evolution, about Internet of Things, cloud and virtualization, and network programming. So let's get right into it with the Internet of Things. The Internet of Things refers to just that, different varying things that will be connected to the internet at some point. We already have so many more items on the internet than we probably could have imagined 20 years ago. We have lights, we have alarm systems, stoves, your car, or at least certain operations of it connected to the internet. They estimate that 50 billion things will be connected by 2020, and who knows what those things will be. 99% of things in general are currently unconnected, so there's a great potential for growth of placing different items on the internet. Things that are on different network infrastructures are being converged to have the same. For instance, your car has a different network infrastructure than a residential building would. Your car's going to have a network infrastructure to control the engine, safety features, communication systems. Your residential building is going to have a network for heating, ventilation, air conditioning, telephone service, so on and so forth. The goal is to have a converged, comprehensive infrastructure that includes comprehensive security, analytics, and management capabilities. The connection of the components into a converged network that uses IoT technologies increases the power of the network to help people improve their daily lives. It's kind of hard to see all those things connected at this point, but the goal is to get there. The Internet of Things connects smart objects to the internet. It connects traditional computer devices as well as untraditional devices. Within the Internet of Things, the communication is machine to machine, enabling communication between machines without human intervention. For example, machine to machine occurs in cars with temperature and oil sensors communicating with an onboard computer. The challenge for the Internet of Things is to securely integrate millions of new things from multiple vendors into existing networks. To help address these changes, Cisco introduced the Internet of Things system to help organizations and industries adopt Internet of Things solutions. The Internet of Things system provides an infrastructure designed to manage large-scale systems of very different endpoints and platforms and the huge amount of data that they create. The Cisco Internet of Things system uses a set of new and existing products and technologies to help reduce the complexity of digitization, if I pronounced that correctly. Here we have the 6 pillars of Internet of Things. The first one being network connectivity, which is basically how you or a company, an industry, connects to the network. Is it access points, switches, firewalls, routers? How do you connect to the network? Basically identifying devices that can be used to provide Internet of Things connectivity to many diverse industries and applications. So all things that provide you network connectivity. Fog computing enables edge devices to run applications locally and make immediate decisions. An example of this would be like an office building being able to lock its doors based on a perceived threat, being able to kill a port, and take action without having to contact the data center. So you'd have devices that are able to make that decision and communicate with other devices in that local network in order to give them orders on how to operate. Also got the security pillar, offer scalable security solutions, enabling an organization to quickly and effectively discover and contain and remedy an attack to minimize damage. Some of the cybersecurity solutions include operational technology, which is hardware and software that keeps power plants running and manages factory process lines. You've got Internet of Things network security, which includes network and perimeter security devices such as switches, routers, firewalls, and Cisco Firepower Next Generation Intrusion Prevention Services, or NGIPS. And you've also got physical security, digital cameras that enable surveillance in a wide variety of environments. They're available in high definition, box and dome, wired and wireless, stationary, pan, tilt, and zoom or PTZ versions. Cameras support MPEG-4 and H.264. Offer efficient network utilization while providing high quality video. Data analytics pillar consists of distributed network infrastructure components and IoT-specific application programming interfaces. To be valuable, the data must be rapidly processed and transformed into actionable intelligence. The management and automation pillar, products can be customized for specific industries to provide enhanced security and control and support. Cisco delivers a broad range of Internet of Things management and automation capabilities throughout the extended network. Cisco management and automation products can be customized for specific industries to provide enhanced security and control and support. The Application and Enablement Platform provides the infrastructure for application hosting and application mobility between cloud and fog computing. The fog environment allows for multiple instances of the application across different end devices and sensors. These instances can communicate with each other for redundancy and data sharing purposes to create business models such as pay-as-you-go consumption for objects, machines, and products. An example of this would be the Cisco IOS X or IOX, which is a combination of the Cisco IOS and Linux. What that is going to allow a router to do is to host applications close to objects that you need to monitor, control, analyze, and optimize. And of course, you'll find more information about those pillars in your readings. There's a couple of videos that go along with them as well that I'm not just going to play here. And we move on to cloud and virtualization. Alright, first we have cloud computing. Cloud computing involves a large number of computers connected through a network that can be physically located anywhere. There are three main cloud computing services. You've got SaaS, or software as a service. The cloud provider is responsible for access to services such as email communication and Office 365 that are delivered over the internet. The users only need to provide their data to get access. Got PaaS, which is Platform as a Service, in which the cloud provider is responsible for access to the development tools and services used to deliver the applications. We've got Infrastructure as a Service, where the cloud provider is responsible for access to the network platform equipment, virtualization network services, and support network infrastructure. Cloud service providers now also offer information technology as a service, which allows customers to extend the capability of IT without requiring investment in new infrastructure, training new personnel, or licensing new software. These services are available on demand and delivered economically to any device anywhere in the world without compromising security or function. We've got four primary cloud models. The first one being public cloud that we see here. Cloud-based applications and services offered in a public cloud are made available to the general population. Services may be free or are offered on a pay-per-use model, such as paying for online storage. For instance, if you have Google Drive, you can get a certain amount for free, or you can pay for a bit more. The public cloud uses the internet to provide services. Then we have private clouds. Cloud-based applications and services offered in a private cloud are intended for a specific organization or entity, such as the government. A private cloud can be set up using the organization's private network. Through this, though this can be expensive to build and maintain, a private cloud can also be managed by an outside organization with strict access security. Which brings us down to hybrid clouds. Hybrid cloud is made up of two or more clouds, part private or part public, for example, where each part remains a distinctive object, but both are connected using a single architecture. Individuals on a hybrid cloud would be able to have degrees of access to various services based on user access rights. And lastly, we have a community cloud. A community cloud is created for exclusive use by a specific community. The differences between public clouds and community clouds are functional needs that have been customized for the community. For example, healthcare organizations must remain compliant with policies and laws that require special authentication and confidentiality. Next, we have virtualization. Virtualization separates the OS from the hardware, allowing multiple operating systems to exist on a single hardware platform. For instance, you could have several servers existing on a single piece of hardware, a web server, email server, SQL server, file server, all running on one piece of hardware. The hypervisor adds an abstraction layer on top of the real physical hardware to create virtual machines which have access to all the hardware of the physical machine, such as CPUs, memory, disk controllers, and NICs. Okay, so I mean, they can't be using all of them using 100% at the same time, but they'll share the resources. All right. Virtualization advantages include less equipment. Like I just said, you could run multiple servers on one single piece of equipment. So you're going to have less equipment involved. Less energy is going to be consumed, lowers monthly power and cooling costs, reduces consumption of energy in general, helps enterprises achieve a smaller carbon footprint. Less space is going to be required because you could have multiple instances or multiple virtual machines running on a single piece of equipment. You have easier prototyping. Self-contained labs operating on isolated networks can be rapidly created for testing and prototyping network deployments. If a mistake is made, an administrator can simply revert to a previous version. The testing environments can be online but isolated from end users. When testing is completed, the servers and systems can be deployed to end users. Faster server provisioning. Creating a virtual server is faster than provisioning a physical server. Increased server uptime. Most server virtualization platforms now offer advanced redundant fault tolerance features such as live migration, storage migration, high availability, and distributed resource scheduling. Improved disaster recovery. Virtualization offers advanced business continuity solutions. It provides hardware abstraction capability so that the recovery site no longer needs to have hardware that is identical to the hardware in the production environment. Most enterprise server virtualization platforms also have software that can help test and automate the failover before a disaster does happen. And then we have legacy support. Virtualization can extend the life of OSs and applications by providing more time for organizations to migrate to newer solutions. There are two approaches to installing a hypervisor. You've got a type 1 or bare metal approach in which the hypervisor is installed directly on the hardware. You sometimes can have a shell of some sort that gets you into the hypervisor, but for all intents and purposes, the hypervisor is directly installed on the hardware, allowing you to have multiple virtual machines hosted on that same piece of hardware. Okay, whether it's multiple operating systems, multiple servers, however it is you want to set it up. The other type is hosted, in which you already have an existing operating system that you're going to install another virtual machine on top of. So you're in Windows, for instance, you want to run a Mac OS. So you would install something like VirtualBox, and you can install Mac OS within a Windows operating system. That is considered a type 2. If you've already loaded into an operating system and then you're going to install another operating system on top of it, that's a type 2 hypervisor. Type 1 hypervisors use a management console that can be used to automatically move, consolidate, and power on and off servers as required. It provides recovery from hardware failure. If a server component fails, the management console automatically and seamlessly moves the VM from VM to another server. The management console for the Cisco Unified Computing System, or UCS, provides management for all software and hardware components in the Cisco UCS. It controls multiple servers and manages resources for thousands of VMs, or is capable of doing so. Something to watch out for is some management consoles can also allow for over-allocation of resources, and that's when basically multiple OS instances are installed, but their memory allocation exceeds the total memory that a server has, so you're going to run into problems there. If you over-allocate within limits because you know that all instances of an OS most likely won't be running at the same time, then you're probably okay. But you kind of have to use your better judgment on that. And we move on to network programming. Network contains two planes, the control plane and the data plane. The control plane is typically regarded as the brains of a device. It is used to make forwarding decisions. The control plane contains layer 2 and layer 3 route forwarding mechanisms such as routing protocol neighbor tables and topology tables, IPv4 and IPv6 routing tables, STP, and the ARP table. Information sent to the control plane is processed by the CPU. The data plane is also called the forwarding plane. This plane is typically the switch fabric connecting the various network ports on a device. The data plane of each device is used to forward traffic flows. Routers and switches use information from the control plane to forward incoming traffic out the appropriate egress interface. Information in the data plane is typically processed by a special data plane processor, such as a digital signal processor or DSP, without the CPU getting involved. SDN virtualizes the network, removing the control plane function from each device and performing it on a centralized controller. So SDN basically takes the control plane from multiple devices and virtualizes it. So you'd have your traditional architecture with your control plane on each device, but the SDN controller is going to need to take that control plane and virtualize it, okay, for each device. One kind of cumulative control plane for all three devices. The SDN framework uses northbound APIs to communicate upstream with applications and southbound APIs to define the behavior of downstream routers and switches. An API, or application programming interface, is a set of standardized requests that define the proper way for an application to request services from another application. The SDN controller uses northbound APIs to communicate upstream with the upstream applications, like we said before. These APIs help network administrators shape traffic and deploy services. The SDN controller also uses southbound APIs to define the behavior of the downstream virtual switches and routers. OpenFlow is the original and widely implemented southbound API. The Open Networking Foundation is responsible for maintaining the OpenFlow standard. Traffic in a modern data center is described as north-south, going between external data center users and the data center servers, also defined as east-west, which means going between data center servers. Going on to controllers, the SDN controller defines the data flows that occur in the SDN data plane. Using the OpenFlow protocol, the controller populates a series of tables implemented in hardware or firmware. The following tables manage the flows of packets through the switch. You got your flow table, these three Table's down here. This table matches incoming packets to a particular flow and specifies the functions that are to be performed on the packets. There may be multiple flow tables that operate in a pipeline fashion, like you see over here. You've got a group table. A flow table may direct a flow to a group table, which may trigger a variety of actions that affect one or more flows. You've got your meter table. The table triggers a variety of performance-related actions on a flow. Cisco developed the application-centric infrastructure to automate the network, accelerate application deployments, and align IT infrastructures to better meet business requirements. There are three core components to this. First being the application network profile, which is a collection of endpoint groups, their connections, and the policies that define those connections. We also have the APIC, or Application Policy Infrastructure Controller. The APIC is considered to be the brains of the ACI architecture. The APIC is a centralized software controller that manages and operates a scalable ACI clustered fabric. It is designed for programmability and centralized management. It translates application policies into network programming. Then we have Cisco Nexus 9000 series switches. These switches provide an application-aware switching fabric and work with an APIC to manage the virtual and physical network infrastructure. The APIC is positioned between the APN and the ACI-enabled network infrastructure. The APIC translates the application requirements into a network configuration to meet those needs. And then down here we have the Cisco APIC Enterprise module, which extends ACI aimed at enterprise and business, enterprise and campus deployments. There are three different basic types of SDN. We've got device-based SDN, where devices are programmable by applications running on the device itself or on a server in the network. Cisco 1PK is an example of device-based SDN. You'll see that here. These other ones wouldn't exist if it was just using device-based SDN. Controller-based SDN, centralized controller that has knowledge of all devices in the network. The applications can interface with the controller responsible for managing devices and manipulating traffic flows throughout the network. The Cisco Open SDN controller is a commercial distribution of Open Daylight. Okay, and if you had that, you'd have both of these, the SDN controller and the policy Open Daylight. They would both exist in controller-based SDN. And policy-based SDN includes an additional policy layer that operates at a higher level of abstraction. No programming skills are required. Cisco APIC-EM is an example of this type of SDN. So you add this application layer on top of it. So you'd have all three in that example. Cisco APIC-EM provides the following features. We've got discovery, supports a discovery functionality that is used to populate the controller's device and host inventory database. We've got device inventory, collects detailed information from devices within the network, including device name, device status, MAC address, IPv4 and v6 addresses, iOS firmware, platform, uptime, and configuration. Got host inventory, collects detailed information from hosts with the network, collects detailed information from hosts within the network, including the host name, user ID, MAC address, IPv4 and v6 addresses, the network attachment point. The topology supports a graphical view of the network topology. The Cisco APIC-EM automatically discovers and maps devices to a physical topology with detailed device-level data. In addition, auto-visualization of Layer 2 and Layer 3 topologies on top of the physical topology provides a granular view for design planning and simplified troubleshooting. That's about it for topology. Policy. The ability to view and control policies across the entire network, including quality of service, policy analysis, the inspection and analysis of network access control policies, the ability to trace application-specific paths between and devices to quickly identify ACLs in use and problem areas, enables ACL change management with easy identification of redundancy, conflicts, and incorrect ordering of access control entries. Incorrect access control list entries are known as shadows. And that is a breakdown of the API-CEM features, and that is a breakdown of Chapter 7. So again, no commands really, just a bunch of concepts, basically reading from the text here. So we got one more chapter left that I do believe we have a couple show troubleshooting commands that we'll discuss, but that's it for Chapter 7, and that's it for now.